Hello and welcome to this presentation describing the STM32H5 security feature called Debug Authentication Control. The following topics will be explained: Introduction to Debug Authentication Control, definition of permissions, use of certificates, handling of permissions, provisioning the debug authentication configuration by using STM32Cube programmer, and description of the ARM platform security architecture or PSA protocol, particularly the Authenticator Debug Access Control or ADAC. Let us start with an introduction to Debug Authentication Control. The debug authentication is one of the most critical security features of the system, considering that with the debugger, the user can access a large part of the system. To control reopening of the debug, the device imposes a debug authentication protocol. If the device is in closed state, the debug state is closed. The debug authentication procedure allows a trusted debugger to reopen access without compromising sensitive information, called the root of trust or ROT. Reopening the debug is possible only if sensitive asset security is ensured and trust zone is enabled. This is called constrained debug, as constraints ensure the security of the ROT information. Alternatively, a partial or full regression mechanism can be used when security of sensitive information cannot be guaranteed. This is called regression, as it ensures removal of the sensitive information before reopening the debug. Partial regression corresponds to releasing non-secure code and assets. The intermediate state, which allows partial regression management, is called NS regression. Full regression corresponds to releasing all codes and assets. The intermediate state allowing full regression management is called regression. The debug authentication configuration must be done only when the product state is provisioning. It cannot be performed when product state is open. The transition to debug authentication state can be performed from provisioning, IROT provisioned, TZ closed and closed product states, as indicated by the green arrows in the figure. The transition is caused by writing the STDA string of characters into the DBG-MCU register and then triggering a reset. The platform security architecture or PSA security model is a specification for securing devices. Recoverable PSA ROT debug applies to devices that can deny access to production PSA secret parameters when in the PSA ROT debug state and can be restored to a fully trustworthy and attestable state on exit if the debug activity hasn't compromised the secured state. Non-recoverable PSA ROT debug applies to devices that are not able to protect the PSA parameters and are not able to ensure that the debug has not compromised the secure state. This type of device should make the PSA parameters permanently inaccessible on entry to debug. The only valid next step is regression of NS regression. Non-PSA ROT debug is restricted to non-secure processing environment and application ROT operation and data. PSA ROT remains intact and trustworthy. During the debug authentication sequence, the product state is not changed. It will be changed depending on the success of the sequence if the request is for one of the regressions. 1. The external host requests to launch the debug authentication protocol via the DBG MCU access port mailbox. The rest of the device is kept under reset. 2. The system, boot and security or SBS selects the STMicroelectronics RSSDA debug authentication library boot address and requests the CPU to be released from reset. 3. The CPU running RSSDA library executes the debug authentication protocol in the system flash memory. If the device is closed, the access port mailbox is closed until RSSDA acknowledges the authentication sequence start request. 4. The authentication method depends on trust zone activation. A. When trust zone is activated, the authentication method is based on certificates. B. When trust zone is disabled, the authentication method is based on password. This method only allows the full regression of the product to be controlled. 5. The above reopenings are effective only when HDPL in SBS HDPL-SR has value equal or superior to the value programmed in DBG-HDPL field in SBS DB GCR register. In the case of an authentication failure, the user is informed through the host interface. The debug authentication library in the system flash memory is available only when HDPL equals 0 or 1. Only this library can perform the steps 3 and 4 described above. To ease the product maintenance in the field, Debug Authentication Control enables the maintenance of the product by activating the debug and makes it possible to manage regressions while considering the security of the sensible information. This implies the following actions. Set the product state in closed state when the product has been configured. When Debug Authentication Control is based on certificates, TZEN enabled, then provision the OEM public key and the SOC mask. Setting the SOC mask to only purpose the non-secure debug and partial and full regression guarantees to be compliant with the ARM PSA security model rather than constrained debug. When the Debug Authentication Control is based on password, TZEN being disabled, then only the hash of the password has to be provisioned. This figure details the various components required both in the host and in the microcontroller to implement the Debug Authentication Control. In the host, the Integrated Development Environment, or IDE, relies on a debug authentication library through the Secure Debug Manager, or SDM. The SDM component asks the Secure Debug Authentication Control for debug access. The Secure Debug Authenticator, or SDA, accepts commands set by the SDM via the debugger mailbox. It issues an authentication challenge and validates the credentials provided in response. Upon successful authentication, the SDA handles the hardware or software aspects of enabling debug access to target resources. In addition, upon request, it can provide the SDM with information about the debug target. This information can be used for discovery and identification purposes, to pass to the credential provider, to present the user with data to make an informed decision when choosing credentials or other purposes. The SDM resides on the debug host and the DA resides on the debug target. The two components establish a logical communication link between themselves. This logical link is routed through the debug client, debug link, and debugger mailbox. The SDA protocol is transported over serial wire debug or JTAG link. The mailbox present in the debug access port is used to exchange messages. This figure details the units present in the debug access port, which is connected to the debug probe by using the port represented on the top. The DAP is based on a unique debug port, or DP, connected to two access ports, or APs, one supporting the APB protocol and the other one supporting the AHB protocol. Note that the resources that the host debugger can access through the APBAP are also accessible from the Cortex-M33 through main bus matrix and core site APBAP. The DBG MCU is therefore accessible from both the remote host debugger and the local Cortex-M33 processor core. Even when the AHBAP is locked, the debugger can access the DBG MCU. This is required to reopen the debug. The DBG MCU includes two 32-bit mailboxes, one per direction, and a status register. In this figure, the locking mechanisms are highlighted. TDO, test debug out signal, can be locked, preventing any communication on JTAG and also serial wire output. Access to AHPAP is locked when debug is locked, preventing debugger access to Cortex-M33 registers as well as memory and peripherals. The lock of the AHBAP can be gated off for security and also power management purposes. The debug authentication signals DBGEN and SPIDEN determine whether debug is permitted in non-secure and possibly secure states. They are generated by the System Configuration, Boot and Security Modules, or SBS. This figure describes the SBS debug control unit. Debug opening depends on the states of inputs on the left of the figure. The debug control unit is configured by the SBS subunits located on the bottom left. The outputs of the debug control unit provides the debug authentication signals to the Cortex-M33 and debug-related IPs such as the DAP. The following inputs control the debug opening: SBS DBG-REC, input signal that a host requests to launch the debug authentication protocol. SBS TZEN informs on the selected platform configuration related to trust zone activation. SBS product state provides the current product state. SBS DBG reset, reset information coming from the RCC and DAP. Configuration of the debug control units is based on the following registers: DBG unlock in SBS DBG-CR, debug unlock when DBG auth HDPL is reached; AP unlock in SBS DBG-CR, access port unlock; DBG auth HDPL in SBS DBG-CR, authenticated debug temporal isolation level defines the HDPL value from which the debug can be opened, value from 1 to 3. DBG auth sec in SBS DBG-CR specifies if the debug reopening is for non-secure only or for both, secure and non-secure. DBG-C lock in SBS DBG-Lock-R locks the current debug configuration, released only by a reset. The outputs of the debug control unit indicate whether debug is locked, debug is only enabled for a non-secure state, or debug is enabled for both non-secure and secure states. This slide and the following one describe debug reopening typical examples. In this one, assumptions are DBG unlock equals 0xb4, enabling debug unlock when HDPL in SBS HDPL SR equals DBG auth HDPL. DBG auth HDPL equals 0x8a, defining HDPL2 as hide protect level at which debug reopens. And DBG auth sec equals 0xb4, enabling debug unlock for secure and non-secure states. Thus, debug for updatable root of trust UROT, non-secure and secure images are reopened. In this example, assumptions are DBG unlock equals 0xb4, enabling debug unlock when HDPL in SBS HDPL SR equals DBG auth HDPL. DBG auth HDPL equals 0x6f, defining HDPL3 as hide protect level at which debug reopens. DBG auth sec equals 0x00, actually different than 0xb4, enabling debug unlock for non-secure state only. Thus, debug for non-secure image is reopened. The type of reset that reopens the debug facilities is configurable, either system reset or power on reset. Reopening debug with NS regression automatically causes the erasure of the NS sectors in user flash and the erasure of option byte keys related to NS application. Epoch NS is incremented. This is a countermeasure against rollback. Then reset is applied. Reopening debug with non-secure and secure regression automatically causes the erasure of the NS sectors in user flash, the erasure of the secure sectors in user flash, and the erasure of option byte keys related to NS application, trust zone, updatable ROT, and immutable ROT. Epoch NS and epoch are incremented. This is a countermeasure against rollback. Then reset is applied. Therefore, all keys and flash contents are lost except resources belonging to the RSS that can never be changed. The next subchapter describes the debug authentication control programmable permissions. For fine-grained access control, the PSAA DAC specification defines a standard mechanism to associate certificates in the chain with a bitmap of logical permissions. The debug host requests access to a set of permissions via the authentication token. The effective permissions are computed by masking requested permissions with permission-limiting constraints from the certificate chain. This mechanism allows for certification authorities to restrict permissions of issued certificates. Transition from closed to open or TZ closed states is a matter of correct product configuration and provisioning. The figure describes the steps required to compute the effective permission. The SOC mask is a static value set by the OEM defining the maximum permissions allowed. It's ended with the permission vector requested by the debug host. The resulting value is also ended with masks set by certificates accumulated in the debug authentication library. The final permission result determines the scope of authentication and restricts permissions that its holder can unlock. The permission mask is programmed into a 128-bit bitmap. Bits 15 down to 0 are related to the ROT core. Bits 31 down to 16 are related to core X. They are reserved for STM32H5. And bits 127 down to 32 are related to specific features. They're also reserved for STM32H5. In the lower half-word, only bits 14, 12, 6 to 4, and 2 to 0 are relevant. Starting point is defined by the SOC permissions that set the maximum allowed permissions. Certificates can bring stronger limitations. This slide describes the lower half-word of the mask. Bits 2 to 0 set the HDPL at which debug can reopen for non-secure debug. Bits 6 to 4 set the HDPL at which debug can reopen for secure debug. Bits 14 and 12 control the regression. Perm EFF is the effective permission resulting from the compute sequence described in this slide. SOC mask is a value to be provisioned by the OEM in the DA config state. SOC mask is a static value corresponding to all features supported by the implementation. The intended use case is to allow the provisioning process of the target to set permanent restrictions on permissions requested by the host, and further, to set the values for those permissions that are restricted. Steps to compute the effective permissions: the host requests a set of debug signals called permrec. The target combines the permission masks present in the certificates of the trust chain called permmask. Finally, the target computes the effective permissions called permf, merging with the SOC programmed permission constraints SOC mask and SOC value. The debug authentication library performs these computations transparently for the end user. This masking mechanism allows a high level of flexibility. The next subchapter introduces debug authentication certificates. When Trust Zone is activated, the authentication method is based on certificates. As soon as a debug certificate chain is fully verified by the device, if the certificate concerns a debug permission, the RSSDA programs the debug opening of the Cortex-M33. Alternatively, the certificate can authorize partial or full regression, allowing debug on a regressed part. The default mechanism for authentication relies on a challenge response protocol. The response to the challenge is a signed authentication token, also called the debug token. A chain of certificates links the key used to sign to the authentication token to a set of one or more trusted anchors. Based on the vendor's needs, the chain can be of arbitrary length, ending in a key directly linked to a programmed root authority. Certificates allow to have a very limited provisioning, but offers a lot of flexibility. Different models to distribute the right to access to different parts of the system can be implemented. However, intermediate certificates also limit the exposure of the most sensitive keys, allowing that those keys can be used less often and protected with added security. The ARM PSA-ADC specification defines a certificate format to build trust chains and offer the flexibility to deal with complex scenarios. Let us describe the contents of a certificate. Scope is limited by fields defining the role: root, intermediate or leaf, SOCID, SOC class. Debug permissions are limited by fields defining the permission request, permission mask, and SOC mask. A token is issued by the host debugger. It allows the microcontroller to authenticate the host through the challenge and response mechanism. This diagram exemplifies a chain of trust. The certificate chain is anchored to the device's root of trust. 4 additional levels are implemented, restricting debug permissions from OEM R&D down to level 1 support field technicians. At each level, an independent pair of keys is required, public and private, to authenticate each stakeholder. ADAC assumes that public keys of trusted authorities have been pre-provisioned on devices and are also available in the ADAC target side code. The certificate is generated by the OEM company. This is basically a structure. This structure that includes the public key is hashed and signed by using the private key. Once generated, the certificate is stored in the OB key related to the minimum HDPL accessible from the OEM. In the OEM company, 2 levels are distinguished: development of secure applications and development of general-purpose embedded software. Isolation is needed between the 2 teams. This is why a separate certificate is generated for the second team. It's obtained by requesting the OEM root to generate a certificate chain. The OEM root generates the certificate that includes the OEM R&D embedded software public key. It's signed by using the OEM root private key. This certificate will be used by the challenge response protocol that enables the debug of OEM embedded software. At each level, a certificate is generated that includes the public key of that level and a signature obtained by the private key of the upper level. A chain of certificates links the key used to sign to the authentication token to a set of 1 or more trusted anchors. Now, after having described permissions and certificates, we can explain how permissions are dynamically processed. 3 examples of permission handling are going to be explained. When a bit equals 1 in the mask, the feature is enabled, else it's disabled. In this example, the debug is requested for temporal isolation level 1, which is the root of trust software executed in HDPL1. SOC mask doesn't provide restrictions. However, permrec and the permission masks contain bits equal to 0. The resulting value permf sets the debug permissions. Bits 2 to 0 equals 0, no HDPL enables opening of non-secure intrusive debug. Bit 6 to 4 equals 0, no HDPL enables opening of secure intrusive debug. Bits 14 and 12 equals 0, no regression is permitted. In this configuration, a debug request from HDPL1 results in a failure. In this scenario, the debug is requested for temporal isolation 3 non-secure HDPL3NS. SOC mask doesn't provide restrictions. The resulting value of permf is bits 2 to 0 equals 4, HDPL3 enables opening of non-secure intrusive debug. Bit 6 to 4 equals 0, no HDPL enables opening of secure intrusive debug. Bits 14 and 12 equals 0, no regression is permitted. In this configuration, a debug request for non-secure application debugging succeeds without regression. In this scenario, the debug is requested for temporal isolation 1 HDPL1. SOC mask disables HDPL1NS and HDPL1S debug opening. The resulting value of permf is bits 2 to 0 equals 0, no HDPL enables opening of non-secure intrusive debug. Bits 6 to 4 equals 0, no HDPL enables opening of secure intrusive debug. Bits 14 and 12 equals 0, no regression is permitted. In this configuration, a debug request for HDPL1 software debugging fails. In this scenario, the debug is requested for temporal isolation 3 non-secure HDPL3NS. SOC mask enables HDPL3NS debug opening. The resulting value of permf, bits 2 to 0 equals 4, HDPL3 enables opening of non-secure intrusive debug. Bits 6 to 4 equals 0, no HDPL enables opening of secure intrusive debug. Bits 14 and 12 equals 0, no regression is permitted. In this configuration, a debug request for HDPL3 non-secure software debugging succeeds without regression. Debug authentication is natively supported by STM32H5 platform. It means that the data used by Security-Debug-Authentication must be provisioned at a defined location in secure key storage area. This will be described in the next slides. On the STM32H5X, the debug authentication configuration must be done only when the product state is provisioning. It cannot be performed when product state is open. The data to provision depend upon the TZEN option byte setting. When moving to later states without provisioning the DA config, the device cannot be regressed anymore. Note that RSS lib encryption option must be set for STM32H57X devices, while RSS lib encryption option must be reset for STM32H56X devices. When Trust Zone is enabled, debug authentication control is based on certificates. When Trust Zone is disabled, debug authentication control is based on passwords. Only the hash of the password has to be provisioned. In all cases, provisioning is done at the beginning of the OBK HDPL1. A tool designed by STMicroelectronics called Trusted Package Creator or TPC is used to generate the OBK, adding a SHA-256 to ensure the integrity of the stored information. TPC is part of the STM32Cube programmer toolset. This slide and the following one contain screenshots of the STM32Cube programmer tool in order to highlight the features related to debug authentication when Trust Zone is enabled. The first step is preparing provisioning. The following informations are required: DA-config XML file describing the OBK region structure. The SHA-256 of the ROT certificate is provided by the file key1root.pem in this example. The SOC mask is defined through a bitmap that can be programmed in the GUI. The OB key is then generated and output in the da-config.obk file. The next step is the provisioning. The microcontroller has to be connected. The previously generated .obk file is selected. Then the user can click on the Start Provisioning dialog to start the programming. This slide and the following one contain screenshots of the STM32Cube programmer tool in order to highlight the features related to debug authentication when Trust Zone is disabled. The first step is preparing provisioning. The following information is required: DA-config with password XML file describing the OBK region structure. The password is directly entered in the GUI. The OB key is then generated and output in the da-config with password.obk file. The next step is the provisioning. The microcontroller has to be connected. The previously generated .obk file is selected. Then the user can click on the Start Provisioning dialog to start the programming. The next subchapter is an overview of the ARM PSA ADAC protocol. The ADAC specification defines the protocol used by the Secure Debug Manager to request debug access from the Secure Debug Authenticator. It's based on 4 layers: debug link, link layer, command protocol, and authentication commands. The ADAC specification covers the following topics: command protocol, debug authentication commands, certificate format, token format. The protocol allows customization, which has been used by STMicroelectronics to design the password mechanism active when Trust Zone is disabled. The following cryptographic algorithms are supported: ECDSA, RSA, EDDSA, Shanghai SM2, CMAC with AES, HMAC with SHA-256. This slide explains the discovery command. The debug host requests information about the debug target used with this command. The requested ID list is discretionary. The target can reply with any set of values that's equal to or a superset of the requested values, excluding any value unavailable on the target or not recognized by the target. If a requested ID list is not included, the target must reply with all available values. Use of this command is optional and is not part of the required authentication command sequence. The required sequence of commands for authentication is as follows. 1. Authentication start. Host requests challenge from target. Its primary purpose is for the target to provide a random 256-bit challenge vector used to prevent replay attacks. 2. Authentication response, 1 or more. This command is used to provide the debug token and additional credentials as part of a complete authentication response to the target. The target validates the provided debug token. If validation fails, the ADAC failure status is returned. In this scenario, a unique certificate is provided by the host, which is the root certificate. When the authentication succeeds, a regression may be necessary and a reset must be applied. The number of certificates used is a decision made by the customer to trade off security versus processing time and management complexity. This example uses 3 certificates. The root certificate signs the intermediate certificate, the intermediate certificate signs the leaf certificate, and the leaf certificate then signs the debug token and challenge vector. In this scenario, trust zone is disabled, authentication is based on password. In order to access the debug authentication feature, the host sends the debug authentication password to the STM32. When the STM32 receives the password, it verifies that it corresponds to the one that's provisioned. When the authentication succeeds, a regression may be necessary and a reset must be applied. Thanks for attending this presentation. You can also refer to UM2238 entitled STM32 Trusted Package Creator Tool Software Description. In addition, you can refer to the following presentations: Security Overview, Secure Data Storage, and Product Lifecycle.